This talk was originally planned for iOS Dev UK, but due to personal circumstances I wasn't able to give it, so I thought I'd put it on YouTube for everyone to enjoy. I'm sure we've all had that conversation. Hey, you're an app developer, I've got a great idea for an app. Well, there's a similar one to be had with people making hardware. I've got an idea for a thing, I just need an app to go with it. We're in a world now where everything is being made smart. It might be your lights, your washing machine, your fridge, or even your toaster. At some point, you're going to be asked to build an app that talks to hardware, and you're going to be asked what the best way to connect them together is. Now, as always, this video is sponsored by PCBWay. More about them later on. So, what are our options? We've got the old school plugging things together with a cable, or we can join Generation Z and cut the cable. We can go wireless. Now, I'm not going to talk too much about the cable options. If you need to go down that route, then you'll be signing up for the Apple MFI program, your hardware will need to be tested by Apple to make sure it works, and you'll need to include a special chip so the phone recognises your hardware. If you don't, then you get this nice pop-up. Accessory may not be supported. The Apple help for this is particularly unhelpful. Your accessory is defective, damaged, or not Apple certified, your accessory isn't supported by your device, or your iOS device has a dirty or damaged connector. As I say, you can solve this by joining the MFI program, but I'm going to assume that for the majority of this it's all a bit too much, so this is out of scope for this talk. Most accessories that use a cable nowadays are just chargers, and even that's going wireless nowadays. So what are our wireless options? Well, we've got two options, Bluetooth or Wi-Fi. We'll cover Bluetooth first. The first thing we need to know is that there are two versions of Bluetooth, Bluetooth Classic and Bluetooth Low Energy, usually shortened to BLE. We'll be talking about BLE. Now, BLE has a really interesting history. Back in 2001, Nokia started developing a low-energy wireless technology based on Bluetooth that they eventually published in 2004 with the name Bluetooth Low End Extensions. They were then joined by Logitech and ST Microelectronics, and with the support of the European Mimosa project, it was publicly released as Wi-Bri in 2006. Finally, in 2010, it was made part of the Bluetooth spec. The first phone to implement this spec was the iPhone 4S in 2011. It's always amazing to me how much work and time goes into getting this kind of technology from research to a production device. Bluetooth Low Energy is an amazing technology. It really is low energy. Depending on your use case, you could be looking at a couple of hundred microamps power consumption on average. To put that into perspective, your iPhone has a battery that is between 2,000 to 3,000 mAh. If we were consuming on average 200 microamps, we'd be able to run for about 10,000 hours. That's more than a year. A lot of use cases you'll see are designed around coin cell batteries. In these cases they are generally asleep for the majority of the time, only occasionally waking up to advertise their presence and see if anyone wants to connect. There are a lot of really nice modules that support Bluetooth Low Energy. Just doing a quick search on RS Online brings up around 250 results, so there's a lot to choose from. These low power modules tend to come packaged with an integrated ARM processor along with a reasonable amount of flash and RAM. They also come with a lot of built-in peripherals, so it's possible to build your entire hardware around these modules. If you do need a bit more processing power, then you can easily couple these modules with more powerful CPUs and still get a low power solution by sleeping the main processor when nothing is happening. Now, the guys who produced the standards for BLE had a dream of compatibility and interoperability. They defined a set of profiles and services for different types of hardware. Manufacturers would produce the hardware that conformed to these services, and then people writing software could code against the profile and know that their software would work with any hardware. Each profile defines a set of services that can be offered up, and each service defines a set of characteristics. For example, a heart rate monitor would implement the heart rate profile. It would provide the heart rate service with three characteristics: the actual heart rate, where the sensor is placed, and the heart rate control point. It would also provide the device information service with the manufacturer's name as a characteristic. If you made a new piece of hardware, then you could publish what services and characteristics your device used. You could even get it made part of the standard, and then people could make compatible hardware and software. They also wanted to create self-describing hardware. As part of your characteristics, you can provide descriptions that provide a human-readable name, what units to use, and how to display the value. Here's a list of all the predefined units. We've got some obvious ones, such as length in metres, mass in kilograms and time in seconds, and we've even got units for the fans of Brexit and the fans of Star Trek. It does look like they tried to get pretty much every SI unit into the spec. The thinking was that people could produce quite generic software and have it work with pretty much any hardware. It would be a beautiful world of cooperation. But what most people do is create their own custom profiles for their specific piece of hardware, and it's probably what you'll end up doing as well. But if you do get the chance to help specify some hardware, please encourage them to add human descriptions and units. So let's try out a live demo. I have set up a very simple device here. We'll use the Chrome DevTools to try and connect to it. Chrome has some quite useful Bluetooth tools, and we should be able to find our device if we start scanning. Now, it can be quite hard to actually find the device because there tend to be a lot of Bluetooth devices around. But if we search for our device name, then we can find it, and then we can drill into it and see what services it offers. So I have a very simple service with 3 characteristics, and I've added some human readable descriptions. So we can read these descriptions and we can see that we have the red channel. So if we write to this channel, we can turn on the red light. And we can turn it off as well. Similarly, I have a green channel, so I can send a value to this. I'll also turn that off. And we have the blue channel as well. So that was interesting, but here's a custom app that I've made that has some sliders that talks directly to the hardware. So we see it's pretty easy to control the brightness of each channel, and we can get some quite nice colours. So that was a pretty simple example. There are some challenges, of course. One of the companies I work with produces these educational robots. One of the problems with Bluetooth devices is that you don't really know which one you are connecting to. Imagine a room full of 20 or 30 children, all with robots, all of them connecting to random robots. It would be carnage. These guys have come up with quite a nice solution to that. When we connect to the robot, it shows us a pattern of LEDs so we can see which robot we've connected to. Here you can see the LEDs on the screen, and these are the LEDs on the robot. It's quite hard to see with this camera because it does get washed out with quite bright lights. Once we're connected, we can make the robot do all sorts of things and move around. He can do a dance, he can wiggle his eyes, and he can raise his arms up and down, and he can walk around. So it's pretty cool. BLE is designed for low power. One of the trade-offs that you generally make to get low power is performance. In the case of BLE, when we talk about performance, we're talking about transmission speed and range. Typically, you are sacrificing both of these when you go low power. However, there are use cases where you do need to transmit a large amount of data over BLE. A typical use case would be doing a firmware upgrade where you might need to transfer a few hundred kilobytes of data. So just how fast can we transmit data over BLE? At this point, I really have to acknowledge a couple of blog posts that dive into this in detail. I'm just going to summarise them, as I'm not going to pretend to have anywhere near the expertise of the blog authors. The first is from 2016, so it's a little bit out of date, but it's full of really interesting information. The second is more up to date and really dives into the details. Both of them are definitely worth reading. So what are the limits on throughput? Well, we have a pretty fundamental limit in Bluetooth 4 of 1 symbol or bit per microsecond. This puts an upper bound on the throughput of 1 megabits per second. It's not possible to go faster than this. We then have a 150 microsecond gap between each packet, and there's an 80-bit ACK packet for each data packet. And then, as always, we have the overhead of the protocol we're using. Now, you might be wondering why we need to have a 150 microsecond gap between packets. Well, BLE is designed for low-cost, simple devices. When you are sending data, the antenna heats up, and this causes it to change its characteristics. The 150 microsecond gap gives it time to cool down, which means your device can be much simpler. Antenna technology is completely amazing nowadays. If you're thinking of your old-style TV aerial, think again. You can build antennas out of PCB traces, and you have these amazing 3D fractal antennas that are absolutely tiny. So the protocol overhead. At the lowest level, we have link layer packets. These have an overhead of 14 bytes and a maximum payload of 27 bytes. Sitting on top of the link layer packets, we have the L2 cap packets. These have an overhead of 4 bytes. And then on top of all of this, we have the attribute protocol packets. By default, These have a payload size or MTU of 23 bytes. This lets them fit inside one link layer packet. By increasing the MTU, you can increase the throughput by removing some of the protocol overhead, but the theoretical maximum you can do is 0.3 megabits per second. So that's what we can do with Bluetooth 4, but technology doesn't stand still. There have been several improvements to the spec. The first came in version 4.2. This lets us extend the data payload in the link layer packet from 27 to 251 bytes. This can give us a throughput of 0.8 megabits per second. The next improvement came in version 5. This lets us increase the symbol rate to 2 megabits per second, giving us a potential 1.4 megabits per second. So that's pretty impressive. It looks like BLE is all we'll ever need. Well, BLE is great when you want to have a device that is used by one person at a time, like a remote-controlled robot or a heart monitor, but sometimes we need something that can be a bit more autonomous or can be controlled by multiple people. It's also short range. You can only really use it when you are close to the device. Also, the device can only talk to other Bluetooth devices. It can't reach out to the internet and pull down data for itself. There's also issues with the software stacks. These generally work, but can be quite buggy. For a long time, the Android Bluetooth APIs were a complete disaster. You are also at the mercy of the hardware manufacturers and their Bluetooth stacks, so getting anywhere near the throughput performance I mentioned earlier is unlikely. The other thing I should mention is that although the link layer of the BLE is reliable, a lot of BLE stacks will silently discard packets if they are overloaded or if there is a contention for resources. So if you are streaming large amounts of data, you may need to build your own reliable protocol on top of BLE. So let's talk about Wi-Fi. This will solve all our problems. First off, let's look at some of the hardware options. There are some really nice modules you can use. A really popular one is the ESP32. This is the dual Wi-Fi and Bluetooth module. It's a really beefy module with a 240 MHz dual-core CPU. You can definitely use this as the basis for your entire product. As with the Bluetooth module we saw earlier, it comes with a lot of built-in peripherals, and once again, if you need to, you can couple the module with a more fully featured processor and just use it to provide Wi-Fi and Bluetooth. So the hardware is easy. But there are some really big challenges. Most devices we're talking about don't have a keyboard, and they usually don't have a screen either. If you are lucky, you might have some indicator LEDs. We don't have any way of entering Wi-Fi credentials. And even if we do get the Wi-Fi credentials set up, there's no easy way to know what IP has been assigned to the device, which makes it quite difficult to do anything with it. Let's deal with the first challenge. What are our options for configuring the Wi-Fi? If you're flashing the device yourself, this is pretty easy. If you've used a Raspberry Pi, then you probably already know about the configuration options when you burn a new version of the OS to SD card. We can tell it the Wi-Fi credentials and set up the username and password for an SSH connection. But if you're shipping ready-made devices to your customers, then you're going to need some other way of setting them up. Now, most routers do support Wi-Fi Protected Setup or WPS in some form. You push the button on your router, and then the device can automatically connect to the network. However, a lot of security-conscious people disable WPS as it's potentially very insecure. And if you're on any kind of corporate or office network, it will definitely be disabled. There's also no guarantee that it will work. I think we're all aware of how bad most Wi-Fi firmware is. Another option is to combine Bluetooth and Wi-Fi. You use the Bluetooth connection to configure the Wi-Fi settings, and then once that has been done, you switch over to Wi-Fi. This can work quite well, but it's quite a lot of extra work, and you do need to use a module that supports both protocols, such as the ESP32. The route most companies take is to have a device that starts up in configuration mode. The device creates its own access point with a captive portal. You then tell your customers to connect to the access point, and you present a form for them to configure the Wi-Fi credentials. So let's show that in action with another live demo. I've got an LED matrix here that I can put into configuration mode by double-clicking its reset button. When it's in configuration mode, it creates its own access point that we can connect to. The AP automatically takes us to a web page where we can configure the wireless network. Once it's set up, it will connect to the network, and it will show us a nice screen showing the IP address. But let's face it, the majority of devices we're dealing with don't have a screen, so we've got a bit of a problem. Our device is connected to our Wi-Fi network, but we don't know where it is. We've got some options. You can get clever and blink out the IP address, but let's face it, that's not very usable. This video is just the device blinking a count of each digit of the IP address, but I've seen some examples where people have used Morse code to blink out Roman numerals. It's a solution, but I'm not sure it's the right one. We can use a fixed IP address. This is a great solution, but it's really only suitable for people like us who can mess around with their routers, and it requires a level of technical competence that the majority of people don't have and honestly don't want to have. Our next option would be to use something like Multicast DNS. This is the technology that underpins Bonjour. It works by broadcasting a query over the network asking for the IP address of a hostname. If a machine on the network has that hostname, then it broadcasts a reply. I've used Wireshark here to capture an MDNS query and response. Here you can see my computer asking what the IP address of matrix.local is. The query gets broadcast to every machine on the network, and here's the reply. It tells us the IP address, and it also tells us how long we should cache it for. MDNS works really well, but for a long time it wasn't supported by the browser on Android, which really limited its use. It is now supported, and you could have always added custom support to your own application, but that is quite a lot of work. The last alternative, of course, is to implement your own discovery mechanism, but you'll find as you start to do this, you just end up re-implementing MDNS, so ultimately pretty pointless. These limitations are often why we see companies creating gateways for their hardware on the internet. It's much easier once the hardware is connected to your Wi-Fi for it to talk to a server in the cloud. Your user will just then go to their account and add whatever hardware they have purchased to it. It will magically start working. This opens up a whole new world of possibilities as you can now access your device from anywhere in the world. It's also a lot easier to automate it with services such as If This Then That. But it does come with a whole host of security and privacy issues, and you now need to maintain a server, as well as some hardware, firmware, and probably a custom app. Now, we talked previously about the trade-offs with BLE and power consumption. Things are different with Wi-Fi. It's not really been designed with low power consumption in mind. With the ESP32, we're looking at around 50 milliamps, jumping up to 0.3 amps when transmitting over Wi-Fi. So with our 2000 mAh battery, we might be able to get a day or so of runtime. However, this really depends on our application. Deep sleep mode can go down to as low as 10 microamps. This little weather display uses an e-paper display and only wakes up every hour to get a new forecast. It runs for about 4 months on one of these 1000 mAh batteries. Pretty impressive stuff. So these are the two options for talking to hardware, Bluetooth and Wi-Fi. Both have strengths and weaknesses. Bluetooth is great, it doesn't require any setup or infrastructure, and you can easily build apps that can connect to your hardware. There's also support coming to browsers. It is still locked behind experimental flags and only supported by a few browsers, but wider support is inevitable. The downside of Bluetooth is it only works if you are close to the device, and it's only suitable for one user at a time. It's also quite low bandwidth relative to Wi-Fi. Wi-Fi opens up a lot of other possibilities. If you have a Wi-Fi enabled device connected to your network, it can pull in data from other services. It also gives you the potential to control it from anywhere in the world. The downside of Wi-Fi is the additional complexity of getting it set up and the fact that it does need a wireless network to connect to. So how about some more alternative solutions? Let's think outside the box. Back when we had headphone jacks, a few companies introduced hardware that plugged into them. Does anybody remember the Senti? It was a little device that plugged into the headphone jack and generated a smell, a real precursor to the future of smelly-vision. For a while there was quite a bit of active development in this area, with people building small breakout boards that harvested power from the audio jack along with data transmission. It's pretty bonkers stuff. Nowadays we don't have headphone jacks, but people are still making use of audio to communicate with hardware. One of my friends has used this technique to solve the problem of setting up Wi-Fi. Let's have a look at this in action.
Press the send button. It does this using sound like this. As you can see, it's now connected.
It brings back memories of the old dial-up days. There are also people using light to transmit information. Here's a system called BlinkUp in action. So what does the code actually look like? It's surprisingly easy to get connected to a Bluetooth device. You start off using the CB Central Manager. This needs to do a bit of setup, which may involve asking the user for permission to use Bluetooth, and if all goes well, it will call back and tell you that it's powered on. You can then tell it to start scanning for peripherals. You can ask it to find all the peripherals nearby, or you can ask it to find only peripherals that are advertising a certain set of services. As it finds peripherals, it will call back with each peripheral it finds. Typically, you present this list to a user and get them to pick the device that you want to connect to. Once you've picked the device, you ask the central manager to connect to it. You can now interrogate the device for the services and characteristics, and then you can read and write from those characteristics. I'm not going to show the actual code, there's plenty of examples out there for you to look at, and it's really just a case of understanding the flow that I've outlined, but it's definitely worth digging into the docs to see what's possible. What does it look like from the actual device's point of view? Here things are a bit more difficult, it will vary depending on the hardware. If you're looking for something simple to play around with, then the Arduino platform is a good place to start. We create a new BTLE server, add some services to it, then we add some characteristics, and then we just start advertising to the world. It really is that simple. It's just a few lines of code, or maybe it's too much code. Let me know in the comments. Thanks for listening, and here's something about PCBWay. They've been sponsoring the channel for some time now, and I've had quite a few PCBs manufactured by them. They also offer CNC and 3D printing, and we'll be doing a couple of projects with that in the near future. Check out the link in the description, they really do offer a great service, and I love working with them.